Solid fuel rocket. A solid fuel rocket carries fuel and oxidizer mixed together inside a solid block known as a propellant grain. Once ignited, the fuel burns continuously until it is exhausted. Because of their simple design, solid rockets are reliable and can remain stored for long periods without maintenance. They are commonly used in military missiles, launch vehicle boosters, and emergency escape systems. Their main limitation is that they cannot easily be shut down or throttled after ignition. Liquid fuel rocket. A liquid fuel rocket stores fuel and oxidizer in separate tanks and pumps them into a combustion chamber. This design allows engineers to control the engine during flight by adjusting or stopping the flow of propellants. Many of the most famous rockets in history, including those used during the early space age, relied on liquid propulsion. Although more complex than solid rockets, they provide greater efficiency and flexibility. Hybrid rocket. A hybrid rocket combines features of both solid and liquid propulsion. Typically, it uses a solid fuel and a liquid oxidizer. Since the two components remain separated until operation, hybrids can be safer to handle and store. They also offer some level of throttle control that traditional solid rockets lack. While not as common as other types, hybrid rockets have been used in experimental spacecraft and research programs. Sounding rocket. A sounding rocket is designed to carry scientific instruments into the upper atmosphere and near space environment. These rockets usually fly on short missions, collecting data before returning to Earth. Researchers use them to study weather, radiation, and atmospheric conditions. Sounding rockets are relatively inexpensive and have played an important role in space science for decades. Orbital rocket. An orbital rocket is built to place satellites, spacecraft, or cargo into orbit around Earth or another celestial body. Reaching orbit requires enormous speed, making these vehicles far more powerful than suborbital rockets. Most orbital launch vehicles use multiple stages to shed weight during flight. They form the backbone of modern space exploration, communications, navigation, and Earth observation. Suborbital rocket. A suborbital rocket travels into space but does not reach the speed needed to remain in orbit. Instead, it follows a curved path and eventually falls back to Earth. These rockets are often used for research missions, technology testing, and space tourism. They provide a way to experience weightlessness and reach space without the complexity of an orbital launch. Multi-stage rocket. A multi-stage rocket consists of two or more sections stacked together. As fuel is consumed, empty stages are detached, allowing the remaining vehicle to become lighter and more efficient. This approach has been used since the earliest days of spaceflight and remains the standard for most major launches today. Without staging, many missions would not be able to carry useful payloads into orbit. Reusable rocket. A reusable rocket is designed to fly more than once. Instead of being discarded after launch, parts of the vehicle return safely for refurbishment and future missions. Advances in guidance systems and landing technology have made reuse increasingly practical. By reducing the need to build entirely new rockets for every flight, reusable systems aim to lower the cost of accessing space. Heavy lift rocket. A heavy lift rocket is built to carry exceptionally large payloads into orbit or beyond Earth. These powerful vehicles are often used for major scientific missions, large satellites, deep space exploration, and crewed lunar programs. Their immense thrust allows them to transport cargo that smaller launch vehicles cannot handle. Super heavy lift rocket. A super heavy lift rocket represents the most powerful class of launch vehicle. These rockets are capable of carrying enormous payloads and supporting large-scale exploration efforts. They are often associated with plans for moon bases, Mars missions, and next-generation space infrastructure. Because of their size and capability, they stand at the forefront of modern rocket development.